Hello, my name is Andy Tran. Here's my EECS presentation on superconductors. Okay, let's go. So, first of all, what is a superconductor? A superconductor is actually a material that has no electrical resistance and expels magnetic fields. There's no power loss through resistance and heat transmission, and it exhibits properties that resemble magnetic field as well. Here's a brief history of superconductors and their discovery as well. So it was first discovered in 1911 when it was found that mercury exhibited no electrical resistance and when it was cooled below 4.2 Kelvin. And Eecs1, Dutch physicist, actually made this discovery when he was experimenting with materials at very low temperatures. And in 1933, Walther Meissner actually discovered that they expelled magnetic fields when cooled below their own critical temperature, and this was coined the Meissner effect. And we'll get into why these are so important in many different industries and fields in the next couple slides. So here we go. First of all, let's get into the types of superconductors. So first of all, type 1 superconductors are usually metallic elements and simple alloys that can achieve superconductivity. They're also named low temperature superconductors as well. And they only have a single critical magnetic field value, which is called Hc. And below this value is usually when they can expel all magnetic fields when cooled below their critical temperature as well. When the applied magnetic field actually surpasses the critical value, these materials lose their superconducting properties and become normal conductors. And type 1 superconductors also have a complete Meissner effect, which means that they can kind of completely expel magnetic fields from their interior. And then we'll continue on to this slide. Type 2 superconductors are also made of more complex materials, and they're also called high temperature superconductors, are kind of because all high temperature superconductors are type 2 superconductors. Not all type 2 superconductors are high temperature superconductors. They usually do have two critical magnetic field values, an upper critical field and a lower critical field as well. They exhibit perfect diamagnetism, similar to type 1 superconductors below the lower critical field. And between the first critical field and the second critical field, they allow partial penetration of magnetic fields, forming a mixed state where some magnetic flux lines penetrate the material while others remain superconducting. And above the second critical field, they become normal conductors. And here's an image of the type 1 and type 2 superconductors you can see on the graph here. And let's get on to the next slide. So types of these high temperature superconductors are also classified as type 2 superconductors, which I said in the previous slide. But don't let the name mislead you, because high temperature superconductors are not materials that superconduct at high temperatures, but at temperatures higher than normal superconducting materials, which means that although it's at a higher temperature than normal superconducting materials, it's still not a high temperature. It's probably still cooled with liquid nitrogen, and or in the case of MRI machines, they're usually cooled with liquid helium, and so these superconductors are not superconductive at really high temperatures, just higher than what a normal superconductor would exhibit superconductive properties at. And let's go on to the commercialization and integration of these superconductors. So the superconductors actually have made its way into the healthcare industry, and some companies have actually integrated superconducting magnets into their MRI machines. improving their imaging capabilities and the resolution in which these MRI machines can see, and also while improving diagnostic accuracy in healthcare, which aids the healthcare professionals in giving the right care to their patients. The MRI magnets are usually made of superconducting materials and creating powerful magnetic fields without dissipating a lot of energy through resistance, because it has no resistance. And the superconducting coils in MRI machines also maintain the high magnetic field strength, and it's needed for achieving detailed and accurate imaging of tissues and organs inside the human body as well. And the absence of resistance also helps the MRI machine maintain the consistency for clear MRI images. So if there were to be if there was resistance, the heat would kind of mess with the image. And superconductors in the energy industry are also effective in making energy transmission more efficient as well, such as superconducting fault current limiters, which are devices that use superconducting materials to manage and control electrical faults in power systems. And these devices can help prevent some increases in current, or help to prevent and contain, sort of in a way. Like these sudden increases in current could break power grids and everything, and it changes itself into a state of superconductivity, and in turn reduces the impact of these faults on the power grid, working as sort of like a fuse, and helps to prevent damage to electrical equipment, increasing reliability and reducing power outages. And we'll go on to the next one. So more superconducting materials have actually made their way into energy efficient systems such as transformers, which step up and step down voltage to reduce power loss through heat, I believe, and motors which offer reduced losses and increase efficiency, as the superconductors do reduce resistance. And superconducting materials in power cables can allow for the transmission of larger amounts of electricity over long distances without substantial losses. So it reduces energy waste during transmission. But there are also issues with cost, cooling, and scaling issues as well. But we'll get onto that in the next slide. Sorry. In the next couple slides. So Japan has also been a front runner in implementing superconducting maglev train technology. They've actually been actively developing and testing a high-speed maglev train system that uses these superconducting magnets for frictionless movement. And the absence of physical contact between the train and the track actually reduces friction and allows for more efficient means of transportation as well. And these superconducting magnets also enable these trains to attain high speeds with minimal energy consumption. And since nothing's touching anything, you don't really need to repair the tracks as much as well. And but there's still scalability and issues, as in this case, in this image, actually this is Japan's way of trying to introduce this maglev train technology into the US, but I think that's kind of iffy right now. And here's its applications in various industries and research. So particle accelerators, like the Large Hadron Collider, actually contain superconducting magnets to guide and control the path of accelerated particles, causing more collisions and better data. Using the magnetic field effect that superconductors exhibit, they can also generate the fields needed to achieve particle acceleration, but also being incredibly energy efficient as well due to their superconducting properties. It also enables scientists to like study fundamental particles, sorry, and conduct experiments within particle physics, also driving discoveries and breakthroughs in fundamental physics research. And then the next part is quantum computing, actually. So superconducting qubits made of superconducting circuits that are cooled to near absolute zero are central to quantum computing, as these quantum bits are superimposed, which means like these bits can, like, the data isn't like being transferred at a set point. It's kind of like superimposed, so it's like the data could be in multiple places at once, which enable quantum gates and operations, which can be manipulated by microwave pulses and magnetic fluxes. Companies like IBM and Google are actually like advancing their superconducting quantum processors, could revolutionize a lot of fields as well. Ooh, sorry. And here's current state-of-the-art superconducting technologies. So researchers in Japan actually developed a monolithic adiabatic integration architecture, which is a superconducting microprocessor with zero electrical resistance. And a lot of other companies, such as Amazon, Google, and IBM, are also um, trying to develop fault-tolerant quantum computers based on superconducting circuits as well. So Amazon actually explores cat qubits for stability against errors. I think this might be related to like Schrodinger's cat. I have no idea. But it focused on bit flips, and this approach is actually less vulnerable to environmental noise. And Google's strategy involves arranging qubits in a two-dimensional checkerboard pattern, and IBM actually uses hexagonal lattices to minimize errors from qubit interactions, which is kind of crazy to think about, actually. And a lot of state-of-the-art superconducting technology is focused for quantum computing is actually focused on reducing like the interference and errors with quantum computing as well. And here's some challenges and limitations and ongoing research. So like the limitations on superconductors are material cost, scalability, maintaining superconducting properties under conditions, and finding a way to like cool them. There used to be actually ongoing research in Korea, I believe, with room temperature superconductor research, but an advancement in room temperature superconductivity was made earlier this year, but it was retracted in November actually. So, and here's a future outlook and to see how superconductors could actually be implemented into different fields as well, such as energy storage, which superconducting energy storage systems, and induction heaters, which superconducting induction heaters would actually be pretty insane. And also with avionics and the and the industry as well. Um, so like it could revolutionize aviation by providing lightweight, high power density systems for electric propulsion, reducing weight and enhancing efficiency as well, and superconducting wind turbines, and medical diagnostics and research. Thank you for watching, and I hope you have a great night.